In this chapter, we will be exploring exponential functions. In this lesson, we'll be looking at exponential function word problems.
Okay, so we're going to take a look at word problems, or at least more specific, or I should say more specific, more general word problems here. So now that we know that the exponential equations are written in the form ab to the x, and we've talked about that, we know that a is basically going to be our y-intercept, okay, and b is going to be the indicator of the growth of the function here, okay, and we've been able to determine from b whether it's increasing or decreasing and what the growth rate is. Okay, remember that your rate, okay, what we did here is we took b and we subtracted 1 from it. If you got a negative, okay, it was decreasing. If you got a positive, it was increasing, and it was increasing by that percentage there. We know that since a is the y-intercept, remember if you make x equal to 0, let's zoom in on that maybe. If you make x equal to 0, b to the 0 is 1, and so you're left with a. I just want you to think about this in context. If we're going to talk about word problems here, we're going to typically let the exponent here be time. And so when time is equal to 0, we get a. That therefore becomes the initial value here. And so now we're going to take a look at some different options here, different ways of looking at this. Problems of growth, let's say bacteria. It could be growth of any kind of a population really. But typically here, if you're talking about it doubling, okay, then we're going to do it like this. We're going to have the initial population, and maybe we'll call it like this. Okay, maybe the P is going to be the final population. We'll do like that. This would be the initial population. Okay, usually like P0 here, but we could even just write it as PI for initial population. And then if we've got a population here that doubles, okay, that's like a 100% change in population. We would put a 2 there, and then in the exponent, you can, if you look at this right here, the way this is written here, it says time that has passed or time that we're being asked about here, and then the denominator here is how often it takes to double. So what happens here is we do t over, in this case we do little p, and that p is going to be the period of growth, how long it takes for this to happen. So it's a ratio here. So if we do this in months, let's say we know that this thing doubles every month. Okay, then if 6 months go by, we do 6 divided by well, actually, sorry, let's say it doubles every 2 months. That probably makes more sense. If we double every 2 months, if 6 months go by, then this exponent here becomes 3. In 6 months, it will have doubled 3 times, and so I multiply by 2 3 times. That's just how you interpret that. If it's tripling, then the only thing that differs here is that we put a 3, okay, in the base here. That represents a 200% increase in the value. So the final amount here is going to equal the initial amount. We would multiply by 3 to the t over the period of growth there. That's not the only thing that we could do with, or the only kind of problems we could look at in terms of growth. There's another thing that we look at called half-life. Okay, if we're looking at radioactive elements, let's say, for example, we talk about the half-life, how long it takes for half of it to decay, and then that's going to stay consistent. So, you know, when you go from, like, let's say 10 grams to 5 grams, then to go to 2.5 grams will take the same amount of time. That also works, for example, we often talk about medicine in the body and how long it lasts, sort of thing. It's a similar sort of question here, but maybe when we talk about amount here, we'll use A. So let's say we've got our final amount here that's going to be equal to our initial amount. I don't know, it just seems, if we're talking about like medication or radioactive elements, it makes more sense to use the word amount. Then we put a half here, but it's the same thing up here. The same exponent will be t over the period of that growth here, where p, again, in this case, is going to refer to the actual half-life. Now, next we've got depreciation versus growth here. We have talked about these already, but now we're going to introduce a formula that's more commonly used here. This is our compound interest equation. Okay, now we've got this p equals 1 minus I here. Now I just want you to remember this. The other day we were working with, or the other lesson here, we were working with b, and we wanted to figure out what the rate of growth would be. So we would do, we would do b minus 1, sorry, is what I wanted to write there, b minus 1, and this would be equal to our I, the growth rate, if you will. Okay, well now notice B in this case is going to equal 1 plus I. Now, remember what happened here. If this was depreciation, then I ended up being negative, which is what this equation here is anticipating. If you've got a depreciation, the rate of that growth here is negative. If you've got appreciation, if the population is growing, then the I was going to be positive. But it's basically the same thing. It's just that now in our equation, we're just being really specific about identifying that growth rate as opposed to the 100% that represents the total population here. So I in this case is the rate of depreciation, and we include the negative in the formula. Here I is the rate of appreciation or the rate of increase, and again we have a positive sign in there to indicate that it's greater than 100% here. Okay, so let's jump into some problems here.
Answer the following questions about a bacterial culture whose initial population is 50 and it doubles in population every 3 days.
Okay, so let's take a quick look at what this question is saying here. Bacterial culture whose initial population is 50. Okay, so obviously we don't know the final population, so we'll put P there. There's our final population. But we know the initial population is 50. It doubles in population every 3 days. Okay, so it's doubling. So we're going to have a 2 in the denominator, in the base of the power there, not the denominator, the base. It doubles every 3 days is what this is saying here. So this is the period of growth here. This is our little p. Little p is 3 here. So obviously t, our time here, has got to be in days. Okay, so just to get consistency to our problem here, so my exponent here would be t over 3. Okay, the time that has passed over the period of that growth here. Now, let's take a quick look here. Which of the following equations correctly gives the population p as a function of time? Oh, well, we just did that. Okay, so let's take a look here. 2 to the 3 over t. No, that's wrong. I need the reciprocal of that. Okay, they switched this one. This would be tripling. Yeah, here's the one. That's the one that I just came up with. Okay, so this is the one that I'm looking for. Next, the question says determine the population after 12 days. Okay, well, let's take a quick look at this. After 12 days, we're just saying t is equal to 12, which is not a big deal. All we got to do now is plug that in. So 50 times 2 to the 12 over 3. Well, 12 over 3 is 4, right? So this is going to be 2 to the 4. Now 2 to the 4 is 16. So 50 times 16, there's going to be 800 present after 12 days. 12 days. Because it doubled every 3 days. Okay, so there you go. That's the number that they're looking for.
Answer the following questions about cesium-137, which has a half-life of 30 years.
Okay, this question right here, now it says the percent of cesium. We should probably just say that cesium-137 has a half-life of 30 years. Okay, so the first question here is, after 10 years, how much is left to the nearest tenth of a percent? Now, I'm being asked in terms of a percent here, so I'm going to get kind of lazy here, kind of clever lazy. My final amount here, I don't know what that's going to be here, but I'm going to let the initial amount be 100. Because if it's 100, whatever my final amount is, I can interpret that as a percentage directly because I'm assuming the initial amount here is 100. Now, the reason why they're not giving you an actual initial amount is because if I'm asking for a percent, it doesn't matter what the initial amount is. Because all you're going to do is compare those two to get a percentage here. And it doesn't matter what the initial amount is. Now, we've got this half-life here. And we know that the half-life was 30 years, so 30 goes in the denominator of my exponent. And I'm given a specific time here, 10 years. So now, I'm going to go to my calculator here. Oops, this is going to be 100. Okay, there's my half-life as a base here to the exponent. And this time I've got 10 divided by 30. And we get 79.37, roughly 79.37. So final amount there is approximately 79.37. So therefore, okay, how much of it is left? We have approximately, whoops, sorry. I don't think I need 2 of those when I'm doing like this. Approximately 79.37% left. Okay? Now, the next question here says, How many years will it take to decay to 25% of its original amount? Okay, well, in this particular case here, 25%, okay, if we do it like this, 25, now I'm supposed to answer this algebraically, okay, so 25 will equal 100 based on the equation that I've just set up here. 1/2 to the, this time I don't know what it is, but I do know that this is 30. Okay, well, in a case like this, algebraically, based on the work that we've done in the past here, I'm assuming that I can write these things as like bases, okay? So let's take a quick look here. Let's try to isolate the power, because that's what we did in the past here. I would divide by 100, and fortunately, 25 over 100 is 1/4. Now, 1/4 is equal to 1/2 to the t over 30 here. Now, I can write these both as powers of 2, but I don't really even need to, because I know that 1/4 is going to be the same as 1/2 squared. 1 squared is 1, 2 squared is 4. Whoops. Sorry, and then I immediately pull that up inadvertently. Now this would be 1/2 to the t over 30. Once I've got power equal to power and the bases are the same, I know that my exponents have to be the same. So I get 2 must equal t over 30, which means t is equal to 60. So therefore, we know that this means 60 years. Okay, it'll take 60 years. Now, let's do this graphically here. And to do that graphically, sorry, just going to get my calculator ready here. Okay, what I'll do here is I will enter in my initial function here, my model. 100 is equal to 1/2. This was going to be equal, 100 times 1/2 to the t divided by 30, or x divided by 30. And I'm looking for where 25% of the original is left. Well, if 100 represents the total amount here, 25 would be 25%. Okay, now I can already tell you that my window settings are not going to match this. Okay, so what we want here is my x-min. I know that my x-min, it doesn't make sense to talk about negative time here. So 0 probably is the most likely minimum here. Now, based on what I just did algebraically, I know that 70 should be a good number for the maximum there. So I'm going to leave that. Okay. However, we'll talk about it in just a second here. Now, my y-min. Okay, well, I started with 100. And it dropped down to 25. I'm going to let 0 be the minimum here, and I'll let the y max here be 100, because remember, the y coordinate is going to refer to the amount that I've got here. So now let's graph that and see what we get. There's my 25%, and there's my point of intersection here. Now, if my x had been smaller than 70, I would have simply noticed that this one was dropping and approaching this one, and I would know that I would have to increase the x max to see a point where they intersect. And so now, remember how I do this. To get my point of intersection, I press second trace to get into the calc menu. I'm going down to my intersect. And if I've only got 2 functions there and only 1 point of intersection, now it's important if there's 2 points of intersection, then I really need to move this closer to that point of intersection so that the calculator knows what I'm referring to. But at this point here, if I just press enter, it jumps to the second curve. It's asking, is this the second curve? Press enter to confirm, and then just press enter to get past the guess. And there it is, 60, 25. So there we go. The answer here was 60. So, and what I did here was y1 was equal to 100 times 1/2 to the x over 30. y2 was equal to 25. And then we use the intersect feature. And we got that x is equal to 60, therefore 60 years. Same thing. There you go.
Answer the following questions about thorium-227, which has a half-life of 18.4 days, and we're beginning with an initial amount of 50 milligrams.
Okay, so question says to algebraically determine when 12.5 milligrams of thorium-227 are remaining. Okay, so we're using our half-life equation, and I mean the variables I had used before. I used the amount final is equal to the amount initial, or the amount not 0 there, times 1/2 to the t over p, the period of growth here. Now, let's plug in the material information that we got here. We know that we're starting with 50. We're trying to figure out when we've got 12.5 remaining. Okay, 12.5 remaining. We got 1/2 here to the t over. T is what we're looking for, and we know that the half-life here is 18.4 days. So that's where everything goes. The initial amount, the final amount, and then the period of the half-life here goes in the denominator of the exponent. Okay, now I am hoping, okay, because this is telling us to do this algebraically, I'm hoping that we get a power of 2 or 1/2 on the other side of the equation here. And actually it turns out we do. When you divide by 50 here, 12.5 divided by 50 ends up being 1/4. Okay, now I just know that because of experience here, but you can divide that out, and if you divided 12.5 by 50, you'd get 0.25. Okay, and so there you go. Now, I know that 1/4 is 1/2 squared. So like I could make both of these powers of 2, but it's just as easy just to say, well, you know, 1/4 is just 1/2 squared. On the right hand side it's 1/2 to the t over 18.4. And so now what I'm going to do is I'm going to, because the powers are the same and the bases are the same, I can state that the exponents are the same. So I know that I'm going to get 2 has got to equal t over 18.4. And then to solve for t, I would just multiply up by that, and I'm going to get 36.8 is equal to t. So when I take a quick look at this, what we got here is it'll take, okay, it will take, what did we get here? 36.8 days to get to that point. Okay? Now, that's an algebraic approach here. This next question is asking something similar. It says, using a graphing calculator to determine when 5 milligrams are remaining to the nearest day. Okay, so if we're going to do this on the calculator, come over here, we're going to plot these things. So first of all, we're going to enter in the equation the way we've got it. We've got 50, starting with 50. We're talking about a half-life. Whoops, sorry, 2 didn't come through. Half-life to the power of x divided by 18.4. Whoops, the decimal didn't come through. There we go. 18.4. And now I'm looking for, to the, what is it, nearest day, to the nearest day, when we get 5 milligrams left over. Now, I'm going to graph this right now with the standard window settings that you get. There's my 5 going through. There, nice and slow. Now I have these things simultaneously graphing. Notice that you can't see the exponential function. So I probably got to address this. So I'm going to go to my window settings. Now, it doesn't make sense to talk about negative time, so I'll just start at 0. I didn't see a point of intersection at 10, which means that the intersection is probably off the screen somewhere. So I'm assuming further on down the screen. So I don't know, let's make that 20. I don't know. I might have to adjust that later. Here's the thing that really didn't match up. Well, it's not possible to have negative mass there. So let's go down to 0. That's the lowest here. Now, my graph here, if you look back at the original expression up here, if I made this y equals 50 times 1/2 to the t over 18.4, I know that 50 is going to be my y-intercept. So I probably want to have my y-max a little bit beyond that. So let's just say 55 here. Let's see what happens when I graph that. There's my y-intercept there at 50. Oh, this is going to take a while because I'm not there yet. So I got to make my x-max a fair bit bigger. Let's maybe make that 50. Let's see what that does. Not quite. Not quite. But it's starting to slow down how much it's come down to. Let's make this up to 70. Let's see if that works. So I hope you're seeing here that it really is just guess and check, even on my part. Okay? I don't know what it's supposed to be. Ah, there they go. Now we got a point of intersection. So now I go into my calc menu here. Second trace gets me my calc menu. I'm going to look for the point of intersection. Calculator asks, is that the first curve? Yep. Am I now in the second curve? Yep. It's going to guess this, and that's okay. Press enter. And it takes me to 61.12. So what we got here, okay, so just to illustrate here, we entered here 50 times 1/2 to the t over 18.4 y2 was 5. Okay, and we found the point of intersection was going to be at 61.1. Now to the nearest day, and when it asks it like that, we're supposed to round just exactly the way it says. So we rounded the nearest day, so it's 61 days. It took just a little over 61 days, but you round that back 61 days to get to that point.
A type of bacteria starts with 380 cells, and after 24 hours, there are 6,080. Determine the doubling time.
Okay, so this question right here is a little different, but just a little different. It's basically the same as a lot of the questions that we've been doing thus far, but this is a little different here. We're starting with 380 cells. Okay, so that's maybe our population here, our initial population, or P0, PI, whatever you want to say here, 380. And after 24 hours, so we're given a period of time that's gone by, now we've got 6,080. So our final population here is 6,080. Determine the doubling time. Now, okay, we're doubling, so the b value here, the base of our exponent is going to be 2, because we're doubling here. The question is, how long does it take to do that? What's the period of time it takes to double? Now, obviously, to go from 380 cells to 6,080 cells, well, we've doubled more than just once there, okay? We've doubled a few times. So we got to figure out how many times it does that. Or maybe not a few times, but we've doubled at least a couple of times. So let's plug all this stuff in here. So the formula we're looking at here is P final is equal to P initial, okay, P naught, give me 2, that's our base here, to the T over P. So I know this is 6,080 is 380 times 2 to the 24 over P. So the only unknown I've got is this guy right here. Now, unless something beautiful happens in my next step here, I'm going to have to go to the calculator to figure this out here. So let's just take a look and see what happens here. I'm hoping that if I isolate my power, I get powers of 2 on both sides here. Here's hoping. So we're going to divide both sides by 380. And 6,080 divided by 380 is, in fact, 16. There it is. Okay, 16 is a power of 2. It's going to be 2 to the 4. So that was really nice that that happened like that. So now I've got 2 to the 4 is equal to 2 to the 24 over P. Power equals power. The bases are the same. So therefore I can conclude that the exponents must be the same. So 4 is equal to 24 divided by P. Now, okay, now just think about that. What number would you divide 24 by to get 4? You should see pretty clearly the answer is P. Now, if you don't like thinking about it like that, you can kind of cross multiply here. 4P is equal to 24. P is equal to 24 over 4. Either way, the answer is P. So the doubling time, because we should always answer the question here, the doubling time is 6 hours.
Answer the following questions about the radioactive element cobalt-60, which can be used to treat cancer patients. It has a half-life of 5.3 years.
Okay, so this first question here is a little bit of a trick question. It says, how long does it take for the sample of cobalt-60 to reduce to half its initial amount? Okay, so we'll set this up here and then we'll talk about what the little trick is here. So we have our final amount is going to be equal to our initial amount. We're talking about a half-life, and this will be to the T over P. Now, you're not told how much you start off with, so it doesn't matter what you put in there. Okay, a lot of times people will default to either like 1 or let's say 100, because then a lot of times you get a percentage, right? Okay, now we know that the half-life here is 5.3 years. So then we have to put it here. We want to reduce down to half its initial amount, so we'll put 50 here. And now when I solve this, the very first thing I'm going to do here is divide by that 100 to isolate the power. And I'm hoping that I get a common base here. And I do. When I divide by 50, I get 1/2 is equal to 1/2 to the T over 5.3. And then on the left-hand side, this is going to be 1/2, and the exponent there is going to be 1. So I've got power equal to power. The bases are the same, so the exponents must be the same. So then I can say that 1 must equal to T over 5.3, and then when I multiply across here, I'll get 5.3 is equal to T. So then the answer here is therefore it takes 5.3 years. But actually, that should have been obvious right from the beginning, because I'm telling you that the half-life is 5.3 years, and then I ask you how long does it take to get to half? Well, that's exactly what a half-life is. You were just told 5.3 years. Okay, so it's more of a conceptual problem than actually one that you're expected to work through. Now let's take a look at the next one here. What percentage of cobalt-60 will remain in the sample after 10 years? Okay, so round to the nearest percent here. So we're looking to find out how much is left. So we're looking for this. Again, it doesn't really matter how much we start with. What the initial amount is, 1/2 to the T over P. So let's say we got 100, okay, 100 left over, because we're looking for the nearest, whoops, sorry, I didn't move that up so you can see it. We're looking for the percentage that's left over, so let's assume that we start with 100. That way, whatever the final amount is, it will already be in the form of a percent. So the final amount will equal 100 times 1/2. Now we're looking at 10 years, and the half-life there is 5.3. So now we'll go to our calculator, and we'll enter that in. 100 times 1/2 to the exponent 10 divided by 5.3. And it looks like we're getting 27 grams left over, 27%. So AF is approximately equal to 27 grams or whatever units that I was using there. So therefore, what are we going to be left with? We're going to be left with 27% is left over. Okay, and there we go. That's what they're asking for. So this last one here asks, determine graphically how long it will take to the nearest tenth of a year. Okay, so we're going to round to the nearest tenth of a year until only 10% of the cobalt remains. All right, well, we've already established the formula here, so we're just going to plug stuff in. For 10% to remain here, I'm going to once again start at 100, throw a 10 in there. This will be 1/2 to the T over that half-life is 5.3. Now this one says do this graphically. So we're going to go to the calculator here. We're going to fill this all in. So here, I've opened this up already. So first of all, we're going to enter in the right-hand side of the equation. So 100 multiplied by 1/2 to the exponent x, because I don't know how much time is going to pass, over 5.3. Now I'm looking for 10% to remain. So I've started at 100. I'm going to take that to 10% is what I'm going to be looking for to be left over with. I'm going to look for where these overlap. Now, right off the top of my head, I don't know what it should be, so I'm going to go just to regular zoom settings and see what I get here. So right there, there's my 10, right? So now what I got to do here is I got to get the other function to come up. What I'll do here is I got to change my window settings. It doesn't make sense to talk about negative time. It also doesn't make sense to talk about negative amount there. So I'm going to put the min and min for both of those to be equal to 0. The max has obviously got to be bigger than 10. I don't know what it's got to be, but I didn't see the other function drop in there, so it's got to make it bigger. Okay, and now we're going to make the maximum here. Because my graph here, or the function here starts at 100 here, we're going to make that maximum 100, just so that I'm hitting the y-intercept so I can see it. Now let's just see what happens here when I do that. Okay, so there's my graph coming down. There's my 10%. All right, good. And so there we do have a point of intersection. So now let's go find our point of intersection. Am I in the first curve? Yep. Second curve? Yep. And then look for it. And we're getting 17.6. So it says to the nearest tenth of a year. Okay, so T was equal to 17.6. Now normally what we want to do here as well is we want to identify what we've entered in. So Y1 will equal 100, 1/2 to the T over 5.3, and Y2 would equal 10. And that's the point of intersection here. So it took 17.6 years to get down to 10%.
A quantity of water contains 1,500 grams of pollutants. Each time water passes through a filter, 8% of the pollutants are removed. Answer the following questions.
Right, well, this first question here should be pretty straightforward. If the water if the filter is removing 8% of pollutants, then what is our rate of decrease? Well, it's going to be 8%. Okay, we're losing 8%. Now, in the equation, though, just remember that in the equation, what that means is that what I'm losing here every step along the way is going to be what I'm left with, sorry, I'm not losing 92%. What I'm left with is 92%. Okay? So I'm losing 8%, which is the rate of decrease. Okay? And I'm going to be left with 92%. Now, 92% is what I want to put into the equation. The equation should identify what's left over, not what I lost. So now when the question says how many filters do you need to reduce the mass of pollutants to less than 150, so we've got this final amount, we've got the initial amount. This time here my base, okay, and actually my exponent here is going to be the number of filters, okay, but my base is going to be 0.92. Okay, now think about that. I want this, that makes sense. The value is less than 1 because it's decreasing, and I want it to be decreasing. I want to be losing, pollutants. And 0.92 is what's left over, what is actually in the, in the water here. So now, here we go. We want to know, we want the pollutants to be less than 150 here. We're told what the beginning is. I'm sorry, I lost that number there. We're told that the initial value is 1,500 grams, 0.92 to the N. We don't know how many filters we're going to need here. How many filters needed to reduce the mass of pollutants to less than 150? So here, we're going to put 150 here. That's our boundary point there, okay? Now granted, we want less than 150. That's going to imply something about what we do with the number of filters. Now, I highly suspect that I'm not going to be able to divide by 1,500 and get some sort of power with a base that I can compare to 0.92. So I'm going to go to the calculator here. We're going to make y1 1,500 0.92 to the n. And we'll make y2 equal to 150, and we'll look for the point of intersection. So y equals 1,500 0.92, because that's how much is left over, to the power of x. There's my variable. And then I'm going to look for where it hits 150. Now, my window settings right now are standard window settings. I'm not going to see anything for a couple of reasons. First of all, because the y-intercept of my first graph here is going to be 1,500. And I'm looking for where it intersects at 150 here. So my window is nowhere near tall enough. I need this to be, if I want to see the y-intercept of that original function here, I need this to be at least 1,500. So I tell you what, let's do our y-max at 1,500. Hopefully this is going to be too crazy here. We don't need the y-min to be negative. It can be positive. I don't need the x-min to be negative. It doesn't make sense to talk about a negative number of filters, because remember, that's what x is. It's going to be the number of filters. So let's graph that. Just change that and see what happens here. So here's my again, here's that 150. That's what I'm looking for. Okay, so right here, this screen here goes up to 10 filters. 10 filters is not enough. So let's go down, I don't know, let's make that 20, see what happens. I'm just glad that when I did the scale up to 1,500, that 150 wasn't so small that you really couldn't make much out of it. Okay, 20 filters doesn't do it. Still not enough here. Let's try 30 filters. And again, I hope you're seeing that I'm just guessing and checking. Okay, there it is. There is a point of intersection there. I can see that. So now I go to my calc menu, go down to intersect. First curve, second curve, let's go past the guess. And I'm getting that x value at the point of intersection is 27.6 filters. Now, now that doesn't make any sense. You can't have 27.6 filters. If you got a filter there or you don't. But what that means is 27 filters wasn't enough to get it to 150. It was really close to 150, but it wasn't 150. So I have to round this up and say, hey, if I want to get at least less than 150, I need 28 filters. That's the number that we're looking for.